Welcome to an example of making a rectangle of maximum area. Suppose that you have 520 feet of rope and want to use it to make a rectangle. What dimensions should you make your rectangle if you want to enclose maximum possible area? Okay, so let's just fool around for a minute before we dive into the details. I want this to make sense for you. So let me just grab a rectangle. Like that one, there's a rectangle. And remember, we have 520 feet of rope, and we're going to make a rectangle out of it. So, I don't know, what if we made this 200 feet long, so that'd be 400, so that leaves us with 120, so this could be 60 and 60. If you add those up, 200, 200, 60, and 60, you get all 520 feet of rope. So there's one rectangle we could make. What would be the area of this rectangle? Remember how to find the area of a rectangle, the space in the middle? It's just length times width, isn't it? It's just one side times the other. So that would be 60 times 200. Either order, doesn't matter. So that would be 12,000 square feet. So there'd be 12,000 square feet. Now what if we did this a little differently? What if instead we made it, I don't know, a little more squarish? How about if we made it a little taller? Here, let me change that plan. Let's make it a little taller. Kind of like that. Well, that looks just as wide as the last one. That can't be, huh? Let's make it a little taller. And not quite as wide. Kind of like that. A little more squarish. It's a little taller, but not as wide. So we're still using the same amount of rope. This time I'm saying let's make this 150. 150. That uses up 300 of the 520, which leaves what? 220. So this would be 110 and 110. I still think that's same total amount of rope. 150, 150, 110, 110. 300 and 220. Yeah, that's still 520. What would be the area of the rectangle now? Well, remember, it's length times width, one side times the other. So 110 times 150. Got to use my calculator here. 110 times 150. I'm getting 16,500, which is more than the 12,000. So notice that both these rectangles use the same total 520 feet of rope to make the rectangle. One of them is wider and more narrow, and the other is more squarish. This is closer to a square, isn't it? Not quite. Square would be the same length and width, but it's closer. 150 by 110. That's closer than 200 by 60. And the area is more area. Closer to a square gives us more area inside. Same perimeter. Same amount of rope going around the rectangle, 520 feet. But if you make the rectangle more closer to a square, you get more area. Notice 16,500 square feet instead of 12,000 square feet. Actual squares, foot by foot squares. Like this would be a foot by foot square. Now mine isn't accurate by the picture, but that's the idea with areas. How many squares, how many square feet? Well, so that's fooling around, but I want to give you a feel for what we're talking about here. Now, with that in mind, let's dive into the actual problem, because we could just keep guessing around forever, but let's just solve the problem now. So let's say we're going to make this rectangle x by y, because we don't know what the dimensions are, do we? We're going to use variables now instead of specific numbers. Then this side would also be x and this would be y. So what do we know? There's 520 total feet of rope. So that means x plus y must be 520, right? The four sides have to all add up. If you start here and you go x, y, it's got to add up to be the 520 feet of rope, because the rope goes around the whole outside of the rectangle. So that means 2x plus 2y is 520. Great. Okay, now what are we trying to maximize? We are trying to maximize, it says right here, maximum area. Maximize area. Now what is the formula for area? Area, as we did a couple times, is length times width, isn't it? So area, length, and width, what are they? Well, it's the x and the y. It doesn't matter which one you call length and width. If you turn the rectangle, it doesn't matter. So just x times y. So the area is x times y, length times width. That's the total space inside the rectangle. That's the area. And we want to maximize that. We want to make that as big as we possibly can. Now, we have two letters, and we have two equations. So you know what we do with that, right? We plug we solve for x or y in the equation and plug in. So technically, this one here is not it's kind of not an equation. You might say, yeah, there's an equal sign. Yeah, but the other side is just a word. So there's really not numbers and letters that are equal to each other. That one's really not an equation, so to speak. It's something we're maximizing. This is definitely an equation. So let's start with that. So you start with that one that's an equation. And so here's step one. Solve for y in the equation. So notice we have technically two equations. In the equation, not the maximum. So not the one you're trying to maximize, the other one. Okay, so let's take 2x plus 2y equals 520. Let's solve for y. So you know what to do here. Subtract 2x from both sides. And what do we get? 2y is 520 minus 2x. Divide through by 2. And this cancels. We get y equals, what's that going to be, 260? Yeah, minus x. So we got y. Now, step 2, plug y into the max equation. I guess they're technically both equations. So I'm going to grab the max equation here, which is simply this. Bring it down here. Area, which we're trying to find maximum area, equals x times y. So plug in right there for y. So that means area, whoops, getting a little scribbly there. Area will be x times, and what's y? 260 minus x. Distribute this. 260x minus x squared. So there's the area formula. Now you see how we've got the area formula in terms of only one letter. So that's much nicer. We can handle it much better when it's in terms of only one letter instead of two. So we take the first equation, solve for y, plug that into the max equation, and now we're trying to maximize the area. Let's rewrite it and put the highest power first. So this will be minus x squared. Let me write that a little better. Minus x squared plus 260. I just reordered it, right? I put the minus x squared in the front. I just want the bigger power in the front. Now, we need to maximize that. What is that, by the way? If we were to graph that, I'm not going to graph the whole thing, but if this was y equals minus x squared plus 260, what kind of graph would that be? That's a parabola, isn't it? If you graphed it, it would be a parabola. It would be something like this. It'd be probably going down, wouldn't it, because of the negative in the front? Remember, the negative in the front means it goes down. So it would be some kind of a parabola, and the vertex is where the max would be. You see, the highest point of the parabola, a U shape that goes down, like this one does because it's got a negative in the front, A U shape going down, opening downward. The vertex, the center, is where the highest point, the maximum, is going to be. So when they want us to maximize this area equation, really what we need to do to maximize this area equation is find the vertex, the center, because that's the highest point in a parabola that goes downward. So what's the formula for the vertex? How do you find the center of a parabola? Remember the formula? It's good to put it in your notes for the exam. Negative b over 2a. And what do I mean by that? I mean negative 1 here, this is a, b is the 260. And if we needed c, it would be 0, but we don't even need c. So remember, a, b, and c are the numbers in front of x squared, x, and the number off to the right. They're not the x's. They're just the numbers in front of the x's. So this will be negative b, negative, and what is b? 260 over 2 times a, and what is a? Negative 1. Just plugged in a, plugged in b. All right, so what's the, and this is the x value. When I shouldn't have said vertex. This is the vertex x value. So the x value, which is negative b over 2a, is what's that come out to be? This is negative 2, so it's, you use your calculator, it's basically it would come out 130 positive, because the two negatives will cancel, 130. So x equals 130. That's the x value of the vertex. Now we want to get the y value. How do we get the y value? Well, we have the relationship up here that we plugged in right there. Y equals 260 minus x, doesn't it? So grab that again. Y equals 260 minus x. So y will equal 260 minus, plug in that 130. Coincidentally, that just comes out 130. So y equals 130. So this is the point over 130, up 130 in the vertex. And what does that mean about real life? That means that x and y are both 130. So the maximum area rectangle is the one where x and y are what? Both 130, aren't they? What do we call a rectangle? Here, let me back that up again. What do we call a rectangle where both the dimensions are the same? We call that a square. So it's a square. What's the area, by the way, of this thing? Length times width, 130 times 130. I don't know. It's, yeah, I think I do know. 16900. 16,900 square feet. That's more than even we had back here. This one is 16,500. This one's the most possible, 16,900. So that is the rectangle of maximum area. It's actually a square. The length and the width have to be the same if you want to make the area inside as big as possible. That's interesting. And so the length should be 130, the width should be 130, and the area is 16,900 square feet. So that's an interesting problem. And so how we solve these is we have two equations, and one of them is our maximum equation, the other is our regular equation. You solve for y in the regular equation, the non-maximum one, then you plug that into the maximum, get one letter, and then you find the maximum of that by finding the vertex, which is the formula negative b over 2a, because the vertex will be the maximum. And that gets you your x, and then you plug back in to get y. There we go.